And here to help lead this discussion on large format modules and their impact is Jonathan Gifford, Editor-in-Chief with PV Magazine Global. Hi, Jonathan.
Yeah, hi David. Thanks very much for having me here today. It's a great pleasure to be with you, and it's been a fantastic event thus far, so that's a credit to you and the PV Magazine USA team. I'm enjoying it thoroughly. Well, we'll kick off this segment with a look at balance of system savings and reliability risks as a result of large format module adoption and insights into directions for future advancements. For this, I'm pleased to introduce Hongbing Feng, the Director of Product Marketing in the US for LONGi. Welcome, Hongbing. Nice to see you again.
Jonathan and David.
Well, fantastic. Welcome to Roundtables USA. Please take it away with your presentation.
Okay. Yeah, I'll focus my presentation on reliability. Right. So first, let me use a few numbers to introduce LONGi. LONGi started in 2000 as a dedicated mono ink and wafer manufacturer, and so for the so by 2020, we shipped more than 58 gigawatt of mono wafers, are the largest mono wafer manufacturer globally, and takes more than 40% of the market share. Since the end of 2014, LONGi expanded into cell and module business. And within 6 years, by 2020, last year, right, we were able to ship 24.5 gigawatts of mono PERC modules globally, became the largest mono module manufacturer. Takes about 19% of the market share. LONGi is also the most bankable solar module brand. And since Q1 of 2020, LONGi is the only AAA rated module manufacturer in this PV module tech bankability rating. Right? And LONGi always consider ourselves as a technology company by consistently invest 5 to 7% of our revenue into R&D. So last year alone, we invested about $400 million US. And so this is the most among all PV manufacturers. This consistently elevated R&D investment really helped LONGi to develop product with a leading performance at a lower cost, which in turn enable us to deliver strong financial performance and strong bankability rating. And first, let's look at the reliability. We think reliability is the foundation for realizing lower LCOE. All the innovative technologies need to demonstrate solid reliability performance before high volume manufacturing implementation. If you look at this simplified LCOE equation, the numerator is composed of all the cost, module cost, BOS, and O&M finance cost. And the denominator is composed of energy yield. It's the electricity generated throughout the lifetime of the PV system. What is not, in the last few years, there's all these innovative technologies introduced into the marketplace, help our customers to reduce cost, either the module cost or BOS cost, and also help to improve energy yield. What is not obvious actually in this equation is the reliability. Reliability, plays a critical role to ensure that energy yield that is can be energy yield can be consistent throughout the lifetime of the system. Without this, if either the module or the component is not reliable, the energy yield can be reduced significantly through the lifetime, which the perceived lower LCOE is not realized. So we think the reliability is the foundation for realizing this lower LCOE. So especially in right now, the PV modules, PV systems are designed to operate, to generate electricity consistently through its lifetime of more than 25 to 30 years, right? And with this, so extreme weathers now become more and more common. So it's very likely, that the PV system may experience some extreme weathers. We need to ensure that we have enough margin in our design that the system can survive through all these extreme weathers and then perform well consistently through its lifetime. So at the LONGi, we take a comprehensive approach on the product quality and reliability. we start from the reliability mindset, start from the module design and material selection. And then, we also use industry-leading technical standards through our process optimization and then reliability testing phase. And for the module production, and we implemented a comprehensive quality management system, as well as the ongoing reliability monitoring program to ensure the produced modules have good quality and reliability. Actually, we do not stop there. And we also actively engage with the third-party labs and then partners, customers, to validate the real-life performance of our product. So here, there are a few major technological innovations adopted in the PV industry that LONGi are leading the way introduced into the marketplace in the last few years. This chart summarizes mono market share change in the last few years, and together with the few major technological innovations. For example, the multi to mono shift, mono PERC and bifacial PERC adoption, and then also the large format cell and the module M6 and M10 standardization. All these advanced technologies help our customer to realize better value of mono technology, which result into massive shift from in the marketplace from multi to mono. Back in 2015, the mono market shares less than 20%. Nowadays, more than 90% of the market is doing mono. Right? And for all these technological innovations, many of these in many places actually do help to improve the reliability. For example, this multi to mono. The mono wafer is more robust material, which can sustain stronger performance through the lifetime of the module of the system. And another example is the bifacial modules made with a double glass construction. Right, I think the extensive third-party tests have extended reliability tests have shown that the double glass bifacial modules, the power degradation through this extended reliability testing are much lower compared to the monofacial glass backsheet construction. In the last couple of years, these large size wafer and then large size modules using large size wafer have been demonstrated as an effective way to help our customer to reduce BOS costs and result in the lower LCOE. But however, this is a large size format modules. If the module size cannot keep increasing, larger and larger. And as actually the module size and then power increase become larger and larger, the BOS savings, the incremental BOS savings become smaller and smaller, has reached a plateau. So at this moment, if you look at all the large format modules made with 182 or 210 millimeter wafer and cells, the analysis have shown that there's not much BOS savings between those different modules with a pretty wide power range from 500 up to 660 watt. So basically, the module size cannot keep increasing without compromising on the reliability risk. The larger format, the ever increasing size on the module will bring up the reliability risk higher. One example is that all the bifacial modules are made with the 2 millimeter plus 2 millimeter glass. There's no support in between the two long frames. So you can imagine when the module size 182.72, the width of the module is about 1.1 meter. And then the 210 60 cell and 66 cell modules are 1.3 meters. Under the same load, yeah.
I need to interrupt if you don't mind. I'm sorry. We can continue with that discussion, but we want to have the full panel join us as well for the discussion. And I'll invite you to stay with us as we move into this larger panel discussion with your consideration. I greatly appreciate it.
Indeed, thanks, Hongbing. And we're going to look deeper into these larger format modules and some of the structural challenges that they face. So do stick around for that. And it's been difficult to look past the emergence of large format modules into global PV markets throughout this year, 400, 500, and even 600 watt plus modules. But as with the concerns we've been hearing about earlier about severe weather and even extreme weather events, there's increasing discussions about the implications for large format module performance over the long term. Concerns are being raised about these new big modules, as we've just heard, in terms of a number of key considerations: wind loads, module currents, and even weight.
Our panelists to discuss these issues have three very different areas of expertise. Hongbin Fang is the Director of Product Marketing at LONGi Solar, who we've heard from just a few minutes ago. Pedro Magalhães is the Director of Global Engineering and R&D at Arctech Solar. And Ben Damiani is the CTO and co-founder of Solar Inventions. Welcome to all of you. And just as a reminder to our live audience, please send through your questions and join in our discussion today. Jonathan.
Yeah, thanks very much, David, and welcome, gentlemen. Thanks for being a part of this discussion. Pedro, I'll come to you straight away. As a tracker supplier, can you give us some kind of indication in terms of market penetration of these large format modules that you're seeing in US projects that you're supplying today?
Sure. So in the US, what we're seeing is like 85% of the projects, at least our projects, utility scale projects, use modules that are like 500 watts plus. We have like about 15% of projects with the old dish, I would say 400 watt panels. Worldwide, in our utility scale projects, pretty much every single one of them is using already modules that are larger than 500 watts.
Okay, and when you're talking about dimensions then, for a tracker supplier, the physical dimensions are a key component and a key part of the equation. What kind of dimensions are you seeing most commonly?
Right, so in terms of dimensions, you know that these large modules are governed by cell size. And, we have like these two different cells, 182 and 210 millimeters. So modules that use 182 millimeter cells, we're seeing typically two sizes, 1.1 by 2.2 meters, and then 1.1 by 2.4. That's for 182 cells. On the 210 cells, these M12s, we are seeing 1.1 by 2.4, 1.3 by 2.1, and 1.3 by 2.4. So I'd say that in the US, we have not been asked to study any projects with this super large 1.3 by 2.4. We've seen only projects with 182 millimeter cells in the US. But in other parts of the world, I'd say that we've seen probably 80% of 182 cells and 20% of 210 cells.
Okay, and then as a tracker supplier, just the last question in this section, how are you responding then to the challenge of these larger dimensions?
Right, so these larger modules increase both tracker dimensions, if you will. I'm talking about chord and length, and that has like structural impact, mainly instability or stability impact on our trackers and our structure. Traditional flexible trackers, which are the type of trackers that people are used to, had to reduce tracker length to cope with these new panels. So a lot of manufacturers that insisted on traditional trackers moved on to dual row trackers. That's basically two rows connected together by a central mechanism. Other manufacturers, and the Arctech is on these other manufacturers' pool, if you will, decided to move on to innovative trackers that are of a rigid construction. We use more fixed points along the torque tube, so we make a very, very rigid tracker, and that allow us to stow the tracker at 0 instead of 30, and have way larger stability because deflections are smaller.
Okay, well, and wind deflections, then I think we're going to address that in more detail, and the wind shear effects also throughout this discussion today. Ben Damiani from Solar Inventions, I'd like to bring you into the discussion here. So Pedro's talked about some of the structural challenges posed by these larger formats. What would you then say about some of the impacts that these wind forces or these additional forces may have on the interior of the module, or the active, productive parts?
Sure. As you go larger, you're going to have greater impact, greater flexing. And with a typical module, you're composed of the silicon layer, the EVA, the solder joints, and the frame and the glass. And each one of those has a different modulus for how it deflects. And so as you get larger, the stress that can come into it, of course, is going to be increased, going out from the wafer size being larger. So some of the ideas on how to address this is to maybe go to thicker glass for both sides of the panel, as well as multi-wire certainly helps, and potentially thicker wafers or how you go, or a stronger frame. You also have longer wires depending on your path length from the module itself. So the current travels through the module and then, of course, comes out through the wires. And all of those factors don't always, contribute to the overall higher efficiency with the panel in operation. Based on, you might have a higher power panel coming off of the production line as you test it in standard conditions, but that might not be fully realized when you do your installation based on what you do. And for the longer length or higher temperature, that the thicker glass could potentially modestly approach or modestly influence, not drastic, but something on the order of maybe 1 degree Celsius.
Yeah, okay, and thicker glass or beefing up the module rail will also have implications when it comes to weight, and then Pedro has to deal with a whole new set of problems on the tracker front. But let's talk about what potential impacts could happen in terms of damage within the module. What have you seen, or what can you foresee?
Certainly more cracking as you go with a larger wafer size. And I think we saw earlier in your presentation, this roundtable for the electroluminescence imaging that can highlight some of these impacts. And certainly within time, you're going to generate, with more flex in the panel, you're going to generate more cracks. The other part of this that comes in with the higher efficiency, or with looking at a larger wafer, when you get more cracks, then you're going to generate more hot points or hot spots, and just the overall integrity of the panel.
Okay, well, Hong Bin, thank you for waiting patiently at this early stage of the discussion. I think you mentioned the figure 400 million in annual R&D spend from LONGi. What's your R&D telling you then? How does that align to some of the issues that both Ben and Pedro have raised in terms of larger format modules?
Yeah, I think this is we have spent a lot of effort when we design these large format modules, right? We have foreseen that definitely, as I showed in my last slide, that when we, 182 72 cell module have a width of 1.1 meter, and the 210 6-row design has a 1.3 meters. When we doing the mechanical loading test, right, under the same load, you realize we found out that the larger format, the 1.3 meter modules showed 40 to 60% higher deformation at the middle of the module, right? Which is going to increase the chance for micro cracking. We have seen that during the test, and also for potential for glass breakage. So these are the issues that we have seen during the testing. The other testing is like a dynamic mechanical loading testing. You will see that with the the modules are held by 4 contact point on the tracker, right? Under the same load, under the same pressure, you will see a higher shear stress, at the 4 contact point, which result into faster fatigue at the contact point, which result into, potentially can result into frame tearing. So this is I think so. We have spent a lot of effort to study these. That's why we think the module cannot go infinitely larger, without increasing, without compromising on the reliability performance.
Yeah, okay. Well, and what about some of the potential solutions on the module level then? What about things like thicker glass? Jenya Maidre from PVEL earlier was saying that quite contrary of that, glass is getting thinner and thinner. What about multi-bus bar in terms of mitigating some of these effects? How effective do you think they are, Hongbin?
Yeah, the multi-bus bar is already implemented, right? But the thicker glass, I think, has the same implications. Will increase the weight. Well, and right now, the modules are already close to, the 600 watt module is already close to 35 kilos, right? So with a thicker glass, you can increase both the weight and also the cost of the module as well, right? Which, we have analyzed that the larger, if you increase getting the module size even larger, higher power, really does not improve on the BOS cost. If the module cost is higher, you end up with a probably higher system cost. In that case, what's the benefit, right? So why do we want to go that route? So we actually think we probably need to stop somewhere here, right? What do we have here? LONGi, we're going to stop at the 182/72 cell. We're not going to make modules larger than this format. Instead, we'll focus on the cell and the module efficiency improvement, right, which can really bring better value for, to reduce the BOS cost as well as the LCOE.
Okay, well, cell efficiencies are not the easiest things to boost in terms of the limit we've more or less reached with PERC technology. But it's encouraging to see a kind of doubling down of effort there. David, in terms of our attendees today, are we getting some questions through?
We are getting some questions indeed, and I wanted to kind of stay with Hongbin for a minute and look a little bit more in depth on performance issues and the performance drops over the life of a module. What are you seeing? What can be expected? And perhaps Ben can chime in on this as well. But can you speak a little bit more expansively on the performance issue?
The performance-wise, basically, I think we have to go through. The industry has developed a pretty sophisticated and well-developed the reliability testing to ensure the modules, the systems are compatible and also can sustain, pretty extended period of performance, right? So I think with the advancement in the latest technology on the PERC, monofacial PERC and bifacial PERC, that the degradation mechanism has been minimized. And so the overall, I think the performance is improving, right? And so, but we have to watch out for these larger format modules to make sure, the module design are adequate and also are tested, right? The performance, during the production, the quality and reliability are verified, right? So that the field, so the module when module installed in the field, the performance can be consistent.
Okay, and Ben, do you have something that you'd like to add to that? What kind of degradation could potential cell cracking as a result of these wins or this additional deflection that's going to occur in the larger formats potentially? What kind of degradation could take place?
Sure. With the solar panel, I think we are all familiar that the performance of the panel can only go as fast as the lead dog or the slowest dog, actually. And so when you have a cracking event inside of a cell, it's going to impact the string that it's in. And that could be bird dropping or shadowing. And so as you go to these larger and larger formats, what that means is each string represents, depending on if it's a half cell or a whole cell, you might have, if you have a 600 watt panel, then each 600 watt panel that's half cell would have 100 watts to 200 watts that it would have for each shading event. So when you had some sort of damage, then you would lose a bigger chunk of power by going to a larger and larger format. So that's one concern that I would have. Same impact with edge shadowing. And then I think even at the cell side, one thing that's going to be interesting, and maybe Hongbin can comment on this, as you go to larger and larger cell formats, initially the wafer thickness is a little increased for processing, and that could also influence the degradation within the wafer. You want the thinner wafer to minimize those impacts of degradation for light-induced degradation in particular. But if you go to a thinner wafer, that's also going to amplify your exposure to the stress of the shear force for the larger format. So it's a tricky question, and something we certainly have to look out for.
Yeah,
These
kind
larger
of
format panels.
a balancing act, I suppose, in terms of the wafer thickness there. Hongbing, did you want to come on the back of that in terms of, what kind of, how to strike that balance with larger wafers and larger formats and wafer thickness and potential LID degradation?
Yeah, definitely. I think the wafer thickness is also on the, it's progressively getting thinner and thinner, right? As we, need to improve on the cost and also, but every step when we reduce the wafer thickness, all these mechanical stability, electrical, performance are verified, right? To ensure, the reliability performance is not compromised. So definitely we need to verify, and that has been, I think the whole industry has been doing pretty well in terms of verify the performance to make sure, the reliability performance, the degradation is not compromised.
Okay, well, thank you. We're talking a lot about the module and the cell. Pedro, I want to bring you back into the discussion here from Architect Trackers. We heard earlier when we were addressing kind of extreme or severe weather events, the importance of kind of a system level approach, particularly when it comes to larger formats. I think Jenya used the phrase that some of these modules are like a sail out there catching the wind, which is not particularly a challenge that any tracker manufacturer would like to face. What kind of role then is stow strategies in terms of dealing with potentially severe winds or stronger winds coming in when you do have larger modules in place?
Right. So when I talk about this topic, I typically talk about the module tracker paradox. With the traditional tracker, what's good for the tracker is bad for the module, and vice versa. For traditional trackers that are very flexible to actually resist wind loading, they need to stow at a steep angle, and that increases the pressure onto the module surface by a lot. So as we see modules growing and growing in size, we're not going to be able to put those modules, in steep angles towards the wind anymore. So these modules require stow at 0 degrees, right? And you can only stow at 0 degrees if you change the way of doing trackers. And that's where these new rigid trackers come in. So the winning solution, I would say, the only reliable solution from now on is to pair these large modules with rigid trackers, because traditional flexible trackers don't cut it anymore.
Well, if you are stowing at 0 degrees, then naturally there's a trade-off when it comes to power output, right? If kind of storm season, I can see power output dropping off. Is that right?
I don't think so. Actually, there are no trade-offs. The only reason why why trackers were not stowing at 0 was because it was not safe for the tracker. The tracker was too flexible, and if you stow at 0, you get into divergence very, very quickly. So trackers couldn't just do it because they used to be inherently flexible structures. So stowing at 0 only brings benefits because the pressure on the panel is lower. Consequently, the pressure that you have to cope designing tracker components is also lower. And when the storm comes, most of the light is diffuse. And the best way to collect diffuse light is actually to look at the whole sky. And you look at the whole sky when you are at 0. If you stow at 45 degrees, let's say, you have like half of the sky on your back. So stowing at 0 increases production, does not decrease production.
And we're talking about bifacial modules as well, quite clearly here.
Right. We're talking about both monofacial and bifacial. Bear in mind, again, if we are talking about a high wind event, that's typically associated with, clouds or a storm of some sort. So direct sunlight is reduced, and the biggest chunk of your source comes from diffuse light. And like I said, the best way of collecting diffuse light is when you are at 0 degrees. Okay, so there are two takeaways that are very important here. You want to use large format modules, you need to control the pressure that gets to those modules, because as both dimensions increase, those modules will not be able to get high pressures. And then two, it's better for your energy production because you're seeing more of the sky, which means that you're collecting more diffuse light.
Yeah, and with high winds generally comes storms, and that means cloud cover and diffuse light.
Right.
Okay, well, we've talked about wind shear, we've talked about right inside the cell, cracking, even wafer thickness, but let's look at module currents. With some of these larger format modules or very large format modules, we're talking about higher currents. I suppose, Ben, I'll go to you first. What kind of reliability issues do you see with higher module currents at the system level, I suppose?
So, I squared R losses. So you have the square of the current times the resistance is what your power loss is going to be. So the change in the wafer format has been pretty dramatic in the last 18 months. And as it turns out, as you go to these larger format wafers, especially up to the M12 size, then when you cut that in half, you're back to the size of a current whole wafer of like M2. So you kind of lose some of the benefit potentially there of the half cut cell, unless you compare it to itself. Of course, having 17 or 18 amps on a wafer would be prohibitive, and you would lose like 30 watts of power in a panel if you didn't cut that in half. So it becomes very imperative. So that's a big concern. So it mandates that you go to half cell on that larger format size.
Okay, well, that's inside the module. Pedro, what about from a BOS perspective? Naturally, at Arctech, you work with some of the EBOS, the electrical balance of systems suppliers as well. Do you think there's challenges that you're seeing in the field with higher module currents?
Right. So we are associated to the BOS choices that are made in plant design. We are not necessarily supplying electrical BOS components, but we have seen that previous EBOS components that have been designed for certain amps don't work anymore. Right? We used to combine strings and get higher currents, and we used to have like 20 amp fuses, 30 amp fuses in these 210 cell modules. We are stringing those modules in 35 modules per string, 38 modules per string. One or two projects even at 40 modules per string, and we have huge currents and lower voltages. So those fuses, all those gauges that we used to see, in the EBOS side now, were pretty much all redesigned. So that was big impact as well. I would say.
Yeah, okay. Well, we've been talking primarily about, well, actually exclusively about the utility scale, I suppose, up until this point. But Ben, you work a lot in the C&I space as well. And of course, this is a huge market in the US. Not only in the US, in so many parts of the world, solar in the rooftop just makes sense. What kind of implications do you see for larger modules, particularly as it pertains to current up on the rooftop?
Particularly as it pertains to current, we would much prefer from an electrical performance standpoint, higher voltage, lower current just means less loss. And in the C&I space, you're going to have some additional challenges with the larger size format as well. We get questions about, people will walk on the panel in residential type applications to blow leaves off the roof or however it might be, and handling a large size format can get challenging if you're putting in a solar canopy. So to stretch out and handle that. And then there's the weight concerns. So there's some challenges we're adjusting to. The bigger power is good at the surface, but can be more problematic when issues come in. So it, still most of the commercial size spaces that we're using will have the installations with the smaller format, the M6, still at this time.
Okay, Okay, but I imagine that the transition to higher powered modules, larger format modules, will be an ongoing one. So we've seen supply of these smaller wafers really pretty much dry up. So there will be more challenges for rooftop installers also to face. Hongbin, I'll let you round out this panel discussion today. You've got a very clear message for the market in terms of what LONGi believes is this optimal size. How are people reacting to this message? How well do you think is the understanding in the market about some of these challenges that you're setting out?
I think many of customers have realized all these challenges, all these reliability concerns and risk. I think this is the market is getting there. And for example, in China, for the bidding, there's a pretty high percentage of the bidding process they uh, eliminate, that prevent high current modules from, being qualified for those, projects, right? So many of customers have realized, but I think we basically need to have more discussions and also more, probably a field performance validations to understand, so that people get real life examples. And I hope people don't learn in the hard way that a few years down the road that you'll see pretty significant energy yield drop from your system. That's a result because of inadequate testing, verification, or just some intrinsic issues with the oversized modules, right? What we really concern is this oversized, the span is 1.3 meters, and that's mechanically just not strong enough to be supported by this 2+2 millimeter glass. And so we hope, basically, on the other hand, the POS cost analysis have indicated that there's not much difference among all these different large size modules. So with the kind of the same BOS, similar BOS savings, but the reliability risk jumps up with the module size increasing much larger. And so that's something we totally against. And so we will focus on the cell and the module efficiency improvement for the next generation technology so that really can bring better value for the customers.
Well, thank you, Jonathan, for leading that interesting discussion. And our thanks also to Hongbin Fang from LONGi, Pedro Magalas from Architect Solar, and Ben Damiani from Solar Inventions.